Now vector functions. Suppose D be a subset of the set of real numbers. से एक real number का set है, उसका एक subset ले लिया D. If to each value of a scalar variable t of t, there corresponds by any rule a unique real number ft, then the rule defines a scalar function of a scalar variable t. यहाँ पर t scalar variable है और ft एक scalar function है. We say that ft is a scalar function of a scalar single variable t. Thus, vector function can be defined as follows. Suppose d be a subset of real numbers. If to each value of a scalar variable t, there corresponds a unique vector gamma is equal to vector ft, then the rule defines a vector function of a scalar variable t. Now see, this is t is a scalar, but this ft is a vector function. We say that vector gamma is equal to vector ft is a vector function of single scalar variable t. In three-dimensional space, this vector function is expressed as gamma is equal to ft, and this is equal to f1ti plus f2tj plus f3tk, where I, j, k, they are unit vectors along coordinate axis x, y, z respectively. We also call it a vector valued function to a vector function. Next, vectors and scalar point functions. If to each point p, x, y, z of a region D in space, there corresponds a unique scalar fp, then fp is called a scalar point function. Generally, we write it as fxyz. Similarly, if to each point p, x, y, z of a region D in space, there corresponds a unique vector fp, then vector fp is called a vector function, vector point function, and we will denote it by vector f x, y, z. See the example. The function f x, y, z defined as f x, y, z is equal to 2x square y square minus 3z square is a scalar point function, whereas the function vector f x, y, z defined as f x, y, z is equal to x square y square I plus 2x square j minus 3x y z square k is a vector point function. So this is the difference between scalar point function and vector point function. So I think it is clear to you. Next, there are some concepts. Limit and continuity of a vector function. Just as we have studied limit and continuity of a real function, similarly, we have limit and continuity of a vector function. See here its definition. Limit. A vector function ft of a single scalar variable t is said to tend a vector limit L. This is a limit vector as t tends to C if for given epsilon greater than 0, however small, there exists a delta greater than 0 such that mod ft minus L is less than epsilon whenever t minus c is less than or equal to delta. We denote it also limit vector ft t tends to c is equal to vector L. So this is the definition of limit of a vector function. Next, we have continuity. A vector function ft of a single scalar variable t is said to be continuous for t is equal to c if for given epsilon greater than 0, however small, there exists a delta greater than 0 such that modulus of vector ft minus fc less than epsilon whenever mod t minus c less than or equal to delta, and in symbol we write it as limit vector ft t tends to c is equal to vector fc. So here limit of the function is equal to the value of the function. This is the difference between limit and continuity. Also, the vector function ft is said to be continuous in a domain D if it is continuous at each and every point t of the domain D. There are certain results for you. See, if limit ft is equal to L, t tends to C, and ft is equal to f1ti plus f2tj plus f3tk, L is equal to L1i plus L2j plus L3k, then limit f1t is your L1, limit f2t is your L2, and limit f3t is your L3. In all, we have t tending to C on all are scalar. But here, this is a vector, this is also vector, this is also vector. Let us see its proof. Given that limit ft is equal to vector L, this is your vector, both are vector. Thus, by definition, for given epsilon greater than 0, there, however small, there exists delta greater than 0 such that modulus of vector ft minus vector L less than epsilon whenever mod t minus c is less than or equal to delta. Thus, for mod t minus c less than or equal to delta, we have right here the value of vector ft and value vector L. So, modulus of f1ti plus f2tj plus f3tk minus L1i plus L2j plus L3k less than epsilon, or it can be written as modulus of f1t minus L1i plus f2t minus L2j plus f3t minus L3k less than epsilon, which implies that for mod t minus c less than or equal to delta, mod f1t minus L1 less than epsilon, mod f2t minus L2 less than epsilon, and mod f3t minus L3 is less than epsilon. So it means limit f1t is L1, limit f2t is L2, and limit f3t is L3. All in all, we have t tending to c. Conversely, suppose limit f1t is your L1 and limit f2t is your L2 and limit f3t is your L3. Let us suppose that for epsilon greater than 0, however small, there exists delta 1, delta 2, delta 3, all are greater than 0, such that mod f1t minus L1 less than epsilon by 3, whenever t minus c less than or equal to delta 1, mod f2 minus L2 less than epsilon by 3, whenever mod t minus c less than or equal to delta 2, mod f3t minus L3 less than epsilon by 3, whenever mod t minus c less than or equal to delta 3. Also, suppose minimum of delta 1, delta 2, and delta 3 be equal to delta. Thus, for mod t minus c less than or equal to delta, we can write modulus of vector ft minus L as modulus of f1t minus L1i plus f2t minus L2j plus f3t minus L3k, which will be less than or equal to mod f1t minus L1 plus mod f2t minus L2 plus mod f3t minus L3, because modulus of I, modulus of j, and modulus of k are equal to 1. Since I, j, k, they are unit vectors. So this is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3 from this. So it is equal to epsilon, means this one modulus of f vector ft minus vector L less than epsilon whenever mod t minus c less than or equal to delta. Thus, limit ft is equal to L when t tends to c. This L is your vector notation. So this statement is also proved. अगर तुम लोगों को कोई क्वेरी है, कोई परेशानी है, कुछ नहीं समझ में आया, तो पूछो मुझे. अब आता है फंडामेंटल थ्योरम ऑन लिमिट्स. See the statement. If vector ft and vector gt are two vector functions of a scalar t, such that limit vector ft is equal to vector L and limit vector gt is equal to vector M, in both t is tending to c, then first limit vector ft plus minus vector gt is equal to vector L plus minus vector M. Limit vector ft into vector gt is equal to vector L into vector M. Limit vector ft cross vector gt. This is not into, this is actually dot product. Limit vector ft cross vector gt is equal to L vector L cross vector M. This cross is vector product. Also, if phi t is any scalar function of t such that limit phi t is equal to small p, then limit phi t vector ft is equal to p into L. Limit vector ft is equal to modulus L when t tends to c. This ft is your taken as modulus of ft. See the its proof. Let ft is vector ft is given as f1ti plus f2tj plus f3tk. gt is given as g1ti plus g2tj plus g3tk. Vector L is given as L1i plus L2j plus L3k, and vector M is given as M1i plus M2j plus M3k. Then it is also given that limit vector ft is equal to vector L and limit vector gt is equal to vector M. Then from the theorem, earlier theorem, as t tends to c, we have limit f1t is equal to L1, limit f2t is equal to L2, limit f3t is equal to L3, limit g1t is M1, limit g2t is M2, limit g3t is M3. Therefore, in case t tending to c, we have limit f1t plus minus g1t is equal to L1 plus minus M1. Limit f2t plus minus g2t is equal to L2 plus minus M2. limit f3t plus minus g3t is equal to L3 plus minus M3. Also limit f1t into g1t is equal to L1 into M1. Limit f2t into g2 is equal to L2 into M2. Limit f3t into g3t is equal to L3 M3. Thus, in the limit as t tending to c, first limit ft plus minus limit vector ft plus minus gt is equal to L1 plus minus M1i plus L2 plus minus M2j plus L3 plus minus M3k. Just substitute the values of vector ft and vector gt in the form of their components. So this will be your vector L plus minus vector M, because it is L1i plus L2j plus L3k plus minus M1i plus M2j plus M3k. So it is vector L plus vector M plus minus. And limit vector ft into dot product vector gt is equal to limit f1g1 plus f2g2 plus f3g3. This is your L1m1 plus L2m2 plus L3m3, and it can be written as vector L dot vector M. And limit vector ft vector product vector gt is equal to limit f2g3 minus g2f3i minus f1g3 minus f3g1j plus f1g2 minus f2g1k. Because if you take the vector product of this one, you will get this expression. This is equal to L2m3 minus m2l3i minus L1m3 minus L3m1j plus L1m2 minus L2m1k. And this is your nothing but vector L cross vector M. If you take the vector product of L and M, you will get this expression. So this is also proved. Next, limit phi t vector ft is equal to limit phi f1i plus phi f2j plus phi f3k. It can be written as p into L1i plus p into L2j plus p into L3k. So it is equal to p into vector L. And similarly, limit modulus of vector ft is equal to limit mod under root f1 square plus f3 square plus f3 square. This is equal to under root L1 square plus L2 square plus L3 square, and this is nothing but modulus of L. So this is all about your fundamental theorem of limits, and this is all about for your today's class. If you need to have any